Hi there, welcome to this video on the atom for grade 10 chemistry in physical sciences. Science has a lot of its own language, so it's important for you to learn how to speak it when you are doing physical sciences. Pause now and check if you know these words and their meanings. Pause again to mark yourself. Now let's have a look at the different atomic models that have evolved over the course of thousands of years. These models are not like Bella Hadid, instead they are more like model airplanes. Each model helps us understand a new aspect about the atom. What is considered the first model is by Democritus, who lived from 470 to 370 BC. Democritus first used the term atomos more than 2,000 years ago to describe the smallest particle that matter is made out of. Atomos in Greek means uncuttable or indivisible. This is because Democritus thought that if you cut a piece of wood in half, cut it in half again, and repeat and repeat and repeat, eventually you won't be able to cut it in half anymore. This would be an uncuttable or indivisible item, like an atom. It wouldn't be until about 2,000 years later when John Dalton pictured the atom as tiny indestructible particles with no internal structure. This was called Dalton's billiard ball model in 1803. In 1897, J.J. Thomson discovered the electron through experimentation. This led to his plum pudding model. The reason why he called it this is because if he imagined the electrons in the atom, he thought that they were surrounded by a positive pudding where the electrons were little plums cut into that pudding. Then, after some time, Ernest Rutherford and Niels Bohr made their own discoveries. Ernest Rutherford said that the atom isn't just like a pudding, instead it has a dense positively charged nucleus with the electrons moving randomly around it. Niels Bohr then took this random movement and made it so that they were instead at fixed distances from that nucleus. This is Bohr's model. You may have learned how to draw Bohr diagrams in grade 8 and grade 9, and we will learn how to do them again this year. In 1924, Louis de Broglie proposed that moving particles like electrons have some properties of waves. Within a few years, evidence was collected to support his idea. This gives you an idea of how the scientific method works in real life. You have your hypothesis, your idea, and over time, evidence is collected in order to either prove or disprove that hypothesis. After that, Erwin Schrödinger, who you will probably know from the phrase Schrödinger's cat, developed mathematical equations to explain the movement of electrons. His work is what leads to the modern-day electron cloud model. James Chadwick, who was a British physicist, confirmed the existence of neutrons, which had no charge. So after all of this time of studying the atom, we discovered, finally, that there is also neutrons as part of the nucleus. Now let's talk about the structure of the atom. If you use the Doc-Scientia textbook, this will be on pages 86 to 89. The atom is made up of constantly moving parts, including a densely packed nucleus containing positive and neutral particles, and electrons, which are negative, orbiting around that nucleus consistently. The positive particles are called protons, and the neutral particles are called neutrons. You can remember this because proton starts with a P and so does positive, and neutron starts with a neut and so does neutral. Both protons and neutrons are called nucleons. In the same way that if you are in South Africa, you are called South African, these two are found in the nucleus, so they are called nucleons. It took a lot of discovery time in order to find out that protons and neutrons and electrons made up the atom. For a long time we thought that it was just the atom and that was it. But then we discovered something even smaller. So, are protons and neutrons fundamental? Are they the smallest thing that exists? No. Actually, physicists have discovered that protons and neutrons themselves are made up of even smaller particles called quarks. These quarks are about the same size as electrons, and as far as we know, quarks are not made up of anything else. but maybe someday we will discover something else. We call these elementary particles. There are many elementary particles that exist, but we're only going to talk about up, down, and the electrons, which are leptons. Protons are positively charged particles found in the atomic nucleus. They were discovered by Ernest Rutherford. Experiments done in the late 1960s and early 1970s showed that protons are made up of other particles called quarks. Photons are made from 2 up quarks and 1 down quark. This is actually what makes them positive. Neutrons are uncharged particles found in the atomic nucleus. These were discovered by James Chadwick in 1932. These are made from 1 up quark and 2 down quarks. This is what makes them neutral. Electrons are the last one, and they are negatively charged particles surrounding the atomic nucleus. They are not made up of quarks, but instead they are elementary particles themselves called leptons. They were discovered by J.J. Thomson in 1897. These are what determine the properties of the atom, and chemical reactions involve sharing or exchanging electrons between different atoms. The nucleus is the central part of the atom. It is composed of the protons and the neutrons, called nucleons. Most of the atomic mass is contained within that nucleus. This was also discovered by Ernest Rutherford. Now we get to the most exciting part about atoms, which is isotopes. Every single element that exists in our universe has isotopes. They have the more stable isotopes and the less stable isotopes, but every element, regardless, has an isotope. Let's have a look at 3 isotopes of hydrogen: hydrogen 1, hydrogen 2, and hydrogen 3. If we take the red circles as protons, we can see that each hydrogen only has 1 proton, because if it didn't, it wouldn't be hydrogen anymore. This is to say that if I gave my first hydrogen a second proton, it would immediately become helium. If I gave that a third proton, it would immediately become lithium. If I gave it a fourth, it would be beryllium, and so on and so forth. The proton number corresponds with the atomic number on the periodic table. This tells you that every single element has a unique number of protons. But the neutrons is what can change. Hydrogen 1 has no neutrons at all. Hydrogen 2 has 1 neutron, and hydrogen 3 has 2. Those are the blue circles that we are looking at. Now we can determine the atomic mass. We measure atomic mass in AMU, or just U. AMU stands for atomic mass units, and U, of course, just stands for units. We can get atomic mass by adding protons and neutrons together. So our hydrogen 1 has 1 plus 0 to get 1. Hydrogen 2 has 1 plus 1 to make 2. And hydrogen 3 has 1 plus 2 to make 3. We can write this in isotopic notation as depicted here, where the top number represents the mass number and the bottom number represents the atomic number. This brings us to our definition of what an isotope actually is. It is atoms of the same element but with different atomic masses. Being the same element means that they have the same number of protons, having different masses coming from having different numbers of neutrons. Electrons do not affect this because they are so small. Let's have another look at a different example of an isotope. Let's look at carbon. Carbon will always have 6 protons as long as it is carbon. If it had 7, it wouldn't be carbon anymore, it would be nitrogen. If it had 5, it wouldn't be carbon anymore, it would be boron. But carbon-12 and carbon-13 are different from each other, not in terms of electrons, but instead in terms of neutrons. Carbon-12 has 6 protons and 6 neutrons, making 6 plus 6, 12. But carbon-13 has 6 protons and 7 neutrons, making it carbon-13. Carbon has 3 naturally occurring isotopes: carbon-12, 13, and 14. Carbon-12 and 13 are relatively stable, while carbon-14 is less stable. This means that over time, carbon-14 will decompose, meaning release its neutrons to become the more stable carbon-12 and carbon-13. This happens and we are able to use it to our advantage in radiocarbon dating. This is something that you might learn about if you do life science. Carbon dating allows us to use the half-life of carbon-14 and the time it takes for that carbon to decompose to determine how long an organism has been dead. That is because carbon-14 is produced naturally by cosmic rays in our atmosphere. And if an organism is no longer actively absorbing new carbon-14, the carbon-14 that is in their body, usually when it's dead, will just decompose over time. Carbon-14 has a half-life about 5,700 years, meaning if we start with, say, 100 grams of carbon-14, we wait 5,700 years, we will find that only 50 grams of it are left. The rest would have become the more stable carbon-14 and carbon-12, unless a new reaction makes carbon-14. You may have noticed over the years that the periodic table includes atomic masses which have decimals. But how can that be if there are protons and neutrons making up that mass? Surely you can't have half a neutron. And that's true. Instead, these decimal figures come from doing an average calculation of the different isotopes. That is, we are taking the weighted average of each isotope rather than just the straightforward average. For example, if I have the natural abundance of chlorine in a ratio where chlorine 35 is about 75.5%, chlorine 37 is about 24.5% of all naturally occurring chlorine, I can use those abundance figures in a calculation along with the atomic masses. First, I would take chlorine 35 and its mass, then multiply that by the percentage. I put it over 100 so that it makes it into that percentage. This gives me 26.4. Then I will take my weighted average of chlorine 37 using the same calculation, and then I add these two figures together to get chlorine's average atomic mass. And you'll see that this is what matches the periodic table. Although this is not entirely accurate because there are much more than just two chlorine isotopes. Now let's have a look at ions. Ions are atoms which have lost or gained electrons. You'll remember that electrons are negatively charged. So if I have lost electrons, I have lost negativity. When I lose negativity, I become positive. We call these ions cations because cats make you feel warm and fuzzy inside. If I have gained electrons, I've become negative because I've gained negativity. We call these atoms anions. Ions do not change the number of protons that each element has. This is because if you were to change the number of protons, you would change the atom that you have. For example, if I took hydrogen and gave it a second proton, we already said it would become helium. If I gave helium another proton, it would become lithium. Now we can have a look at the electrons, which is what actually does change. Electrons can either be lost or gained through chemical reactions or through friction and by other means. Hydrogen, when it is neutral, has one electron. That is because one proton and one electron cancel each other out, protons being positive and electrons being negative. So I can kind of think of this as saying 1 minus 1 gives me 0. This 0 figure is my net charge. Net charge is another way of saying total charge. Then I can look at hydrogen plus 1. Hydrogen plus 1 has lost its electron, so it has 0 of them. This is like saying 1 minus 0 gives me 1. Then I have the last one, hydrogen negative 1. Hydrogen negative 1 has 2 electrons. So this is like saying 1 minus 2, which gives me minus 1. And you can see we write it next to the atom. Pause now and try to figure out these 4 different problems. Pause again to mark your answers. Thank you for watching. Hopefully this helped you in some way.